All right, so it looks like I'm going to be away from you for a little while longer. But that's okay. It's no big deal. I still get to teach you. So we're going to move on. And you should have a packet with this as your cover sheet. We're going to go in now to the ins and outs of these topographic maps. And you may hear other people pronounce them topographic maps, topographic maps. It's almost like Caribbean. Either way works. You'll hear people in the field call them one of either. Doesn't really matter. I learned them as topographic maps, so I call them just that. Sometimes for short, you'll hear people call them topos. So I think that's probably why it sticks with me. But in any event, let's learn about these maps. Now I understand that you've been working on some of these principles, so now it's time to organize our thoughts and put these right thoughts in our head and try to maybe smooth out the rougher edges. So let's start. Right here, so open that packet. You're going to be writing some things down, so make sure you have a pencil, pen, something that you can use. On these maps, we've seen these lines. You've drawn these lines, either by doing the water activity where you poured the water in the container, and you were able to stop every so often and see what type of shape that made around the landscape, and then you traced that faithfully on your paper. Or you've gotten to experience the gizmos, the building topographic maps, reading topographic maps, or you got to have an experience in the stations that many of you got to experience. You've seen these lines on the map. Well, these are called contour lines, and these lines represent equal areas of elevation. And as you progress one line to the next line to the next line to the next line, your elevation is changing. Could be going up, could be going down, but the elevation is changing. So as we look at this indication here, this small diagram, there's a point here that represents 76 feet. Well, and another point over here that represents 123 feet. One of the things that you'll need to know is what this number actually means. If you were to look at a topographic map of our school's campus, you would see numbers like 806, 812, 820, just on our campus. Well, what does that mean? 800 feet. There's not a single place where I can walk around here and get to the edge of wherever we live and look down and see 800 feet. There's nowhere anywhere near here that I can look down and see 800 to 0. So where's the 0? If we live at 800 feet, and we do, roughly, well then, where's the 0? Well, these numbers represent feet above sea level. So if you see a map that has a 0 on it, that means you've reached the ocean. So any number higher than 0 is that many feet above sea level. So this point here is 76 feet above sea level, and this is 123 feet above sea level. But I wanted you to grab your pencil right now, because this means then that if we have 1, 2, 3 lines between them, if I'm standing, let's say I'm going to stand right here. So let's say I'm standing right here, and I move 3 steps in this direction. How has my elevation changed? Have I walked uphill? Have I walked downhill? The answer is I've walked downhill, because in this map, heading toward the higher number means you're going higher in elevation. So I want you to write something down. This line most likely is a line that represents 80 feet. So this is 80 feet. So I want you to label that line. This is 80. And judging by how close this 123-foot mark is, probably this next line is going to represent another 20 feet in elevation. So this is 80, and then that one's 100, and then this one's probably 120. So write those things down. And we're going to kind of use this idea of elevations and then elevations at regular intervals as we scroll through some of these charts and maps. So contour lines are these lines that you're going to see on the maps, and they are separate points of higher elevation from points of lower elevation. And it also means that everywhere on that line, just like you saw in the water demonstration and in the map demonstration and in the stations, everywhere on that line that you stand, you're going to be at that exact sea level, at that exact elevation. So if this line represents 120 feet, that means everywhere exactly on this line is also 120 feet. It's when you cross lines that you change elevation. But when you walk with the lines, you don't change elevation. And we'll get to that here in a little bit. Okay, next page. All points on one contour line have the same elevation. So there you go. If I'm standing here, I'm at 140. If I walk the line and I stop right there, I'm still at 140. Maybe I walk another mile this way and I stop right there. As long as I am walking on that line, my elevation, upsy or downsy, has not changed. But the next line down here, and I say down because it's down the page, says 160 feet. So if I am standing right here and I take 3 steps this way, how has my elevation changed? Have I walked uphill? Have I walked downhill? Well, looking at the diagram here, looking at this map, I'm walking from 140 feet toward 160 feet. So I'm actually walking uphill. If there are points in between these lines, and there will be, they will usually be marked by how exactly their elevation is different from the lines. So this one says 147, this says 153. Notice that the 140 line does not touch 147. 140 line is only going to touch the areas on the map that are exactly 140 feet above sea level. In the same way with the 160. Okay. As you saw in a lot of your experiences and demonstrations, these contour lines will never cross each other. They won't cross 1, they won't cross 3, they won't cross 5, they won't cross any. Because a spot on a map can't be, let's say this line is 100 feet. And let's say this line right here is 120 feet. A spot on a map cannot both be 100 feet above sea level and 120 feet above sea level. One point, one place in time can't be 2 different elevations. It's going to be one or the other, right? And this 100-foot line can't all of a sudden be greater than 120 feet. And at the same time, it can't be less, this 100-foot line can't now be less than 80 feet. Okay? Lines are going to be drawn where those elevations occur. So this line can't be more than this one and at the same time less than this one. The lines will never cross. They're always going to be by themselves, concentric, closed loops. Even if they don't close on the map you're looking at. Maybe they go off the map somewhere. Well, at some point they come back on the map. You just might not have a close enough view of the map. But all these contour lines are closed loops. And they never cross each other. Even if they don't close loop on the map you're looking at, they still close somewhere. They come all the way back around. So, they never cross one another. It's very important to know. Okay, now we talked about this when we experienced the Martian demonstration at the beginning of our first class, which I believe was Monday. No, it was Tuesday. Okay, so we noticed that in our experiences, we noticed that as we were walking towards a mountain, or what we thought was a mountain or a hill, those lines got closer together. and the circles got smaller and smaller and smaller. But the lines getting closer together told us that we were approaching a steep slope. Now, it doesn't matter if you're looking at the slope going down or looking at the slope to go up. Still, lines close together represent a steep slope. So a lot of elevation is changing in a very short distance of the land that you would walk. Okay? Lots of elevation change in a short distance. That's what a steep slope is. So if you're wanting to do a sled hill, and you're wanting to find a sled hill, looking at a topographic map, you want to find those lines that are closer together. Now, I don't know if you want to find one that looks like this. Maybe if you were a paratrooper, perhaps, maybe that would be fun. But lines so close together that they touch, they won't cross, but they can touch. That tells you that so much elevation is changing in such a short distance that that's a vertical cliff. That's like a Grand Canyon, like you're looking straight up, or you're looking at the edge going straight, this star represents this individual here. And, a couple steps this way, and then they're looking over the edge at a pretty steep drop. So, lines that are so close together that they touch represent a vertical cliff. But even though they touch, they won't cross. When the lines are spaced out evenly, and they're not so compact, they're spread out and spaced apart, then what you're looking at there is a gradual uniform slope. This is the slope we were trying to walk when we started our classes with the Martian crew demonstration of your rover ran out of power and you had to walk yourselves back to base. What's the safest or what's the best path to get you there? What's the best route? Well, in order to be safe, right? So nobody turns an ankle or anything. In order to be safe, you want to try to find where those lines are spread apart as much as possible, because you're going to be finding that elevation that you're walking is going to be nice and gradual and uniform. So lines that are spaced out farther apart and uniformly spaced, evenly spaced, that indicates a uniform slope. So this person right here, from above looking down, is this person right here experiencing a more gentle slope. Okay, this is where we're going to have to kind of slow down for a minute, because this is where the first of two places where students are going to trip up when they're trying to learn this stuff for the first time, and that is to try to calculate something that will definitely be on your quiz. Okay, and it's called the contour interval. Okay. Now back here, you don't have to turn your page, but I want us to review something that we already covered. Back here, I said, judging by the 76 foot and this 123 foot mark, that this was probably 80, this was probably 100, this is probably 120. Okay, how did I do that? Okay, well, I was guessing what the contour interval was for each of these lines. There's nothing on this map that tells me what it is. I just looked at the numbers on either side and tried to divide it up evenly in my head. And that's how most of us do it, actually. But it can be figured mathematically. You don't just have to guess at it. And careful, because there's going to be some that you're going to guess and you're going to guess wrong. So the contour interval is the difference in elevation between two lines that are next to each other. Okay, so we're trying to figure out, not all these lines have their markings, their elevation numbers on them. So how do we know how much elevation each line is? Well, you're going to need to find the contour interval of the map. And once you've found the CI, it's also listed right here, CI, contour interval. Once you've found this contour interval, it is true for everywhere on the map. So once you've figured out the value of each additional line, which in this case is 20 feet, that's true for the entire map. Anywhere you go on that map. Now, what if you pull out a different map and its CI is 10 feet? Okay, that's fine. So everywhere on that map, When you see an additional line, that's a change in elevation of 10 feet. So every map has a contour interval, but not every map has the same contour interval. And here's why. Imagine having to draw a topographic map of Worthington. Okay. Now imagine having to try to draw a map, a contour map, a topographic map of the Grand Canyon. There's a lot more elevation change in the Grand Canyon map than there would be in the Worthington map. So if you're going to get down there and try to show detail on the Worthington map, you can get away with having a contour interval of 5 feet. Every new line is 5 feet. If you tried to draw a topographic map of the Grand Canyon where every new line on that map is only 5 feet of elevation change, your whole map would be one huge solid marking of black all over the map, and you wouldn't be able to tell one line from another. So in an area where you have a lot of elevation change in a short distance, you're going to make that map readable by having your lines represent larger elevation changes. So that's why every map has its own contour interval, because it depends on, am I going to draw a map of an area that's very upsy-downsy? I'm going to need to make sure that when people read this map, they can still see it, instead of having it so covered with lines that you can't really tell what's what. So every map has a contour interval, but not every map has the same one. So every map, you have to determine what the contour interval is. And here's how you do it. Usually, it's found somewhere on the map, and it kind of looks like this. Now, spoiler alert, for your first couple maps that you're going to do with us in class, you'll see the contour interval there. However, you're going to have to get good at learning how to find it mathematically, because we're going to not give it to you on these maps anymore. But you can use the clues on the maps to help you find it. And here's how you do that. First, on the map, find any two numbers where there's no other numbers in between them. Okay? So on this map, I see a 200, and the next number I see that's its neighbor is a 500. So, so the first thing I do is I'm going to subtract. Find the difference between these two numbers. And by the way, there are no negatives. So it's absolute value minus absolute value. Everything's positives, okay? Because remember, all these numbers are above sea level. They're all above 0, right? So they're all positives. Okay, so 500 minus 200 is 300. So what I'm saying is that from this line all the way to that line, the elevation has changed by 300 feet. Now, but I need some more information so that I can find my contour interval. So I've got this 300 feet. Okay, that's good. So that's going to be a part of the equation. First, you subtract the two numbers that you can find that are closest to each other on the map without any other numbers in between them. Now, I've done that. This is 300 feet. So I put 300 feet right here. Now, next thing I have to do is I have to start at one of these, the 200 or the 500 line. I have to start there. And then what I have to do is I have to figure out how many pieces has that 300-foot elevation change been cut into by these lines on the map. So I need to count the lines. Okay, so I'm going to start at the 200 or the 500. Okay, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I stop here, which is 15. So that 300-foot elevation change on this map has been cut by 15 lines. So if I take 300 divided by 15 lines, that's going to tell me that each line represents an elevation change of 20 feet. So that literally means if I wanted to write all my numbers between 200 and 500 now, since I know the value of every additional line, I could do that. So that'd be 220, 240, 260, 280, 300, 320, 340, 360, 380, 400, okay? And so on until you got to 500. That's how you can check to make sure that your math is accurate. But you're really only doing two things. You're doing a difference, which is a subtraction, and then you're doing a division, and you're done. Okay, it's very easy to do. You're going to be tempted to just look at it and go, 40, okay, 40 or 80 or 100. You're going to be tempted to look at it and just guess. Well, you might get it correct, but you might also get it wrong. So I encourage you, every single time you encounter a topographic map that you have to find the CI, I encourage you to use this method. You'll never get it wrong if you use this method. Okay? So again, start by the 200 or start at the 500, doesn't matter, and then start counting the lines 1, 2, 3, 4, 5, and so on all the way here. So you're counting this area that's been cut by how many lines, do the simple division, and you will have found the contour interval. Okay? Some are easy to spot. You can just look at it and go, oh, it's 0 and 100 and it's split by 5 lines. Okay, well, that's 20. Some of them are easy to determine real quick in your head. Others aren't. So I encourage you to use this mathematical formula every single time. Every single time. You will never get it wrong. I'm telling you right now, some of you are going to write down 100 for a map that's really 80, and you're going to wish you hadn't because you didn't do the mathematical formula to make sure that you got it right. I'm telling you now, you're going to miss it if you don't do the mathematical formula. Okay. Now you notice that on this map here, this is a map that has a lot of elevation change over a short distance. And it's going to be really, really tough to try to follow these lines all the way around the map. I could very easily lose what elevation I'm trying to find. So the cartographers have started to use, and they've been doing this for a long, long time now, on these maps, where they darken every 5th or 4th line. It's usually one or the other. Typically, it's the 5th line. But every 4 or 5 lines, they will darken it, just to kind of let you know, like, oh, okay, that's another 100, or that's another 50, or that's another 10. And they'll darken those in a regular sequential order. That's a way for you to kind of keep track of the elevation change. And we call those darkened lines index contours. Just makes it easier for you to follow and do your elevation calculation. Okay, because right now you're just looking at a really small square right here, but if you had a whole map that took up your whole work table, your student desk in front of you, there are maps that are that large. And if you're trying to trace something around, 3 or 4 feet of table, it'd be really difficult to maintain your elevation on the map because you'd be losing yourself in all these lines that are all the same color and all the same thickness. So they've made this a helpful visual by darkening every 4th or 5th line, and those are called index contours. And you'll see those on the maps, and I think you'll find that they're helpful in keeping you on track. Okay. I know I said earlier there's 2 things that people get tripped up on. Well, contour interval, after you know the mathematical formula and after you've kind of just committed yourself to using that formula to find the contour interval, you really don't get tripped up on that one anymore. But there are still 2 that you're going to get tripped up on if you're not careful. And this one is the one that's still going to have the potential to trip you up even after you've figured out contour intervals. And that's called, it's how streams and rivers interact with these contour lines. So you might come up across a map that looks like this, and there aren't really any numbers printed on the map where you're looking. And there's a stream there, and the stream is going to be indicated by a thin blue line or a thin dotted blue line, or dots and then a straight and then dots and then a straight. Those are usually called intermittent streams. So it means like when it rains really hard, there's water running there, but when it's not raining anymore, then that one dries up. But there's a lot of little markings on your maps like that. And when a stream or a river cuts through the ground, right, it's going to make the contour lines bend in the shape of a V. And the reason for that is the river's cutting into, it's carving, it's eroding into the ground. And it's cutting more and more away. It's deepening and it's deepening and it's deepening and it's carving. So you have these cut channels in the ground. They're cut in V shapes because that's where the water is really being active and carving out the bottom, the river bottom. So the contour lines they're drawn to follow that shape of the ground where the river has cut through. So you're looking at a map like this, but there's no numbers. Well, how am I supposed to know which way is uphill, which way is downhill? I'm trying to get from, maybe on my map, I've got to get from here all the way down to here. Like, what do? Is this uphill? Is this downhill? I mean, I'm supposed to be radioing helicopter rescuers to find some lost hikers, and I can't tell them on this map where to go uphill or downhill because I don't know what I'm looking at here. Well, there's a key, there's a little trick. And rivers and streams, they all work and behave in the same way when it comes to these contour lines. And here's how they work. As it says up here, I want you to underline this. Okay, underline, contour lines curve or point like a V in the upstream direction. Okay, that means the tips of these V's are pointing in the uphill or upstream direction. So right here is a V. The contour line has been curved or pointed into a V shape. This contour line has been curved into a V shape. Okay, here's a V. Here's a V. Here's a V. Okay, you can see them going onto this part of the map. So the tips of the V's point in the uphill direction. And you might be thinking, okay, why did you tell us that this is something that we were going to get tripped up on? This sounds simple. It is. But you're going to remember this part, and you're not going to remember the answer to my next question. At least some of you won't. And that's what makes it difficult. Because you're going to remember one part of this explanation, but you're going to forget the second part of the explanation, or you're going to get them confused. So listen carefully. The tips of the V's are always going to point uphill. Great. Which way is uphill? This way. Great. Good. Now, which way is this river flowing? If you said this way, then you live on some distant planet where gravity does not affect water. Okay? Many of us are going to switch these answers to mean that, oh, something that it doesn't mean. Okay? The tips of the V's are pointing uphill this way, which means uphill is that way. Water flows downhill. So the water is flowing in the opposite direction that the V's are pointing. Okay? The tips of the V's point uphill. Your change in elevation upward is that way. But the water doesn't go uphill. It goes this way. It goes downhill. Okay? You've got to keep that part straight. I promise you, you're going to get a picture that looks kind of like this, and the question's going to be, it's not going to be where's upstream. The question's just going to be, in which direction is this river flowing? And a good 40 to 60% of you are going to go, well, it's flowing that way, because that way's uphill. No, that way's uphill, but water flows downhill. Okay? So don't get confused. All right, now this is going to lead us into the other thing that's going to trip you up. But we're almost done. Okay? Not everywhere on our planet do we have just hills that you can either, kind of walk up or walk down and move on to the next hill. There are also craters or caved-in depressions or calderas where volcanoes are, or where they used to be, or craters of long ancient meteor or meteorite impacts. How would we show those on the map? Well, this is how you would show that. Okay? So a series of closed contour lines represents a hill. We know that. Except when these closed contour lines have what we call hatchered marks on them, that means that you're done walking uphill, and now you're walking down into a pit or into a ditch, an enclosed like impact crater or caldera or something. So that's how we designate kind of like a bunker, like in golf. Like that's a place where the land goes whoop and then it comes back out again. Now, you're going to be asked, once you find the contour interval on the map, you're going to be asked to label every single contour line before you go answer any other questions. And I'm telling you now, you're going to come across some of these. And you're going to be tempted to do something incorrect. So let me show you how to do it correctly first. You have found the contour interval. It is 20 feet. Okay. And you correctly recognize this as a closed depression, and you know that the elevation is going down. But fight with all your heart, fight with all your will and all your might. Do not call this one 680. Don't. It's still 700. Here's why. You're here, you're walking along, you're walking uphill. You cross the 700-foot mark. You are still walking uphill. At some point up here, we reach the top of our hill. We don't know exactly where because there's not, as you'll see coming up, there's not something called a benchmark here. But we've reached the top of the hill. Now, the top of the hill is not another, as this says, another 20 feet. So on this map, right, every new 20 feet, there's a new line. Okay? Well, there's not another line up here that says 720. So what we've done is we've walked, we've gotten to a certain place up here, but not another 20 feet. And then we've started coming back downhill. And to the first 20-foot downhill we get to is the 700-foot that we crossed coming uphill. We've hit the top. Now we're coming back downhill. We hit 700 again. And then 680. And then 660. So closed depression marks are a little tricky to label for contours because you're going to be tempted to write, well, I know this is downhill and I know the contour interval is 20, so a line downhill from 700 to 680. No. You're still walking uphill. Somewhere up here you're going to reach the top of the hill and you're going to start walking into the depression. And the first line you're going to get to is that 700 elevation, but you're going to be going downhill into the depression. Into the depression, not a depression. Let's not go into a depression. Okay. So that's how we label lines in a closed depression, like a crater or a caldera or a pit. You look for the hatchered lines, and basically it's just kind of an automatic response. You look at the last line you crossed before you get to your first hatchered mark and just write that same number there. That's just a quick tip for you. And then every 20 feet you're subtracting until you get to the last line in the caldera or last line in the depression. So not every place on our planet is an uphill. Right? We have pits and things too, so we have to show those on the map. So that's how you do that. Now, here's that benchmark I was telling you about. Benchmark is something important that occurs, but it doesn't occur on a contour line proper. Like right here. Well, this tells us that the very top of this hill is at 772, and it marks it with this X. It's called a benchmark. Whenever you see an X with a number next to it, that's telling you this is an accurate elevation for this spot right here. And if you're seeing it in a situation like this, that usually means, hey, you know what? You started right here at 700, and every line is a new 20 feet. So this is 700, 720, 740, 760. Now the top of the hill is right there, and it happens to be 772. So at this point right here, anywhere you take one step off of that point right there, any step in any direction, now you're going downhill again. Now, this is still 760. This is 740. This is 720. Okay? And right here happens to be, maybe this was a spot for some historic event in battle or something, in a war or something. But they're like, hey, this is also a benchmark for something important that happened. And this spot happens to be 713 feet. Okay? We call these benchmarks. Something important happened there, or it's the top of a feature or the bottom of a feature that doesn't exactly exist at an even 720, 40, 60, whatever. So they will label it for you. They'll put it there, and they'll say, hey, this is 772, or hey, this over here, this one spot where, I don't know, some president was shot at or something, or you know, whatever. This is elevation is 713. So that's what benchmarks are. Okay. The lowest point on the map, well, water always seeks to find the lowest point. So where you're finding water is where your low points are going to be. Also, remember how I was telling you earlier, like all these numbers are above sea level, right? So if you happen to see a 0, like, I don't know, right there, then that means that's the beach and that's the ocean. You notice how there are no more lines, you know, under this 0 line. There's no more lines under there. That's water. You've hit the beach. You've hit the ocean shore. Okay? So the low points on a map, if you can find 0, you're at the ocean. So it doesn't get any lower than the ocean. Or if you found water, usually, right, water, since this is uphill, water is flowing downhill this way. So usually your lowest point of elevation on a map is where the water is leaving your map. Usually that's also a low point. So look for those things. The lowest spot on the downhill side of a stream or river, or you can look for a 0 elevation mark. That'll tell you you've hit the ocean. Okay, here's the other area of the two where you could get tripped up, and it is finding the minimum elevation of an area, and it doesn't give you the benchmark. You just have to figure it out. Or it is the maximum elevation of an area. So let's see if I can move this out of the way. Did I get it? Maybe not. Okay, well that's all right if it's there. So here's what we do. If you're trying to find the very, very, very bottom of a depression, but it's not benchmarked, but it's asking you, what's the lowest elevation it could be down in the bottom of that depression? Well, here's what you do. You won't know for sure, but the question is, what's the minimum elevation it could be? Remember, minimum means lowest. So when you're walking down to the bottom of this pit, and you've walked downhill, 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 and you've reached the bottom, and you're getting ready to come back out. When you've reached the bottom, what's the lowest elevation it could be? And here's what you do. Remember, the contour interval of this map is 20 feet. So every line is an additional, or it's a different 20 feet. So you're walking uphill, cross 900, you hit the top somewhere, and you're coming back downhill into 900, 880, 860. Now, there's no more lines at the center. Okay? This is the last contour line right here. So the answer isn't 840. If it was 840, there'd be another line in there that would say 840. So what's the minimum it could be? The minimum elevation, right, of a depression is 1 foot more than if we had another line drawn on the map. 1 foot more. In other words, it's down almost to a new elevation line, but not quite. So it's not 840 going downhill. It's a foot above it. So the minimum elevation it could be is 841 feet. Remember, if it was 840, we'd have another contour line drawn in there. So it's 1 foot higher than what a new line would be drawn on the map. That's how to find the minimum elevation on anywhere on a map that doesn't have a benchmark. Well, what if I asked you, could you find the maximum elevation of a hill that was not benchmarked? And you're really just using the same methodology. So you've got an X right there, but there's no number on it. Well, how am I going to know what the maximum possible elevation could be? Well, I'm starting at 300. My contour elevation, or my contour interval is 20. So here's 300. I go to 320, 340, 360. This is not 380, right? If it was 380, there'd be another line drawn in there because this contour interval tells us that every 20 feet gets a new line. So this can't be 380. But the maximum, the highest it could be without getting to 380 is 1 foot less than 380, or 379. This minimum and maximum elevation is going to take some practice. But just remember, the way that you can figure it out is look at your contour interval. Okay, every line has to be another 20 feet. This here can't be 380 because we don't have another line drawn. So it's got to be 1 foot away from what a new line would be. And in this case, since I'm being asked about the maximum elevation, it can't be 381. I'm going uphill. I'd be going I'd be going higher than a 380 line. So this has to be 379. It's like we're getting up pretty high, but we're not quite to a 380 line. So that'd be 379 right there. Okay. That's a lot to pack in. You will be set free real soon to start working on maps from the bottom up. Okay, so it's very important that you keep hold of this packet, that you write down the things that you're supposed to, that you highlight the things you need, that you box or circle or underline the things that you need to know. And you're going to need to use these when you're diving into your maps. Keep your packets with you. You're going to get to use them on your maps until you get the hang of how to decipher these. Okay, that's the end. All right, so good luck with all of your cartographizing and topographic mapping, and I'll see you soon.